What specific problem does TokenSkip aim to solve within the context of chain of thought, COT, prompting in large language models?
TokenSkip aims to solve the problem of inefficiency in chain of thought, COT, prompting by addressing token redundancy within COT outputs in large language models, LLMs. The research identifies that not every token in a COT sequence contributes equally to deriving the final answer, leading to unnecessary computational overhead and prolonged response times. By empirically analyzing the semantic importance of tokens, TokenSkip enables LLMs to skip less important tokens and learn shortcuts between critical reasoning tokens, facilitating controllable COT compression with adjustable ratios. This approach not only reduces the number of tokens used, but also maintains robust reasoning performance, as demonstrated by minimal performance drops even with significant token reductions. Ultimately, TokenSkip enhances COT efficiency while preserving the interpretability and reasoning capabilities of LLMs.
How does the TokenSkip method work? Illustrate the process step by step, focusing on the token pruning, training, and inference phases.
The TokenSkip method operates through a systematic process involving token pruning, training, and inference phases. In the token pruning phase, TokenSkip first calculates the semantic importance of each token in a chain of thought, COT trajectory, using a metric derived from LLMLINGUA2. Tokens are then ranked based on their importance, and a threshold is established according to a desired compression ratio, allowing only the most important tokens to be retained in the compressed COT. During the training phase, high-quality COT trajectories are filtered, and each trajectory is pruned according to a randomly selected compression ratio, with the training samples formatted to include the compressed COT and the corresponding answer. Finally, in the inference phase, TokenSkip utilizes autoregressive decoding, where the model predicts the output sequence based on the input prompt, effectively skipping unimportant tokens during the reasoning process, thus enhancing efficiency while maintaining reasoning capabilities. This structured approach allows TokenSkip to achieve significant reductions in token usage without substantial performance degradation.
Could you provide a simple example to demonstrate how TokenSkip compresses a COT output while retaining critical reasoning tokens?
TokenSkip compresses a chain of thought, COT output by identifying and retaining only the most critical reasoning tokens while pruning less important ones. For instance, in a COT sequence, numeric values and mathematical equations are prioritized for retention due to their significant contribution to the final answer. In contrast, semantic connectors like of and the, which contribute minimally to reasoning, are skipped. This process allows TokenSkip to maintain the integrity of the reasoning steps without reducing the number of steps themselves. As a result, the compressed COT retains essential information while achieving a reduction in token usage, exemplified by a 40% reduction in tokens for the 5 to 14B instruct model on the GSM-8K dataset with minimal performance drop.
What are the primary benefits of using TokenSkip compared to traditional methods of handling token compression in COT sequences?
The primary benefits of using TokenSkip compared to traditional methods, such as prompt-based reduction and truncation, include its ability to maintain reasoning performance while effectively compressing COT sequences. TokenSkip allows LLMs to skip less important tokens based on their semantic importance, achieving a significant reduction in token usage, up to 40% with less than a 0.4% performance drop on the GSM-8K dataset. In contrast, prompt-based reduction often fails to meet specified compression ratios, while truncation leads to substantial accuracy drops, with a 79% decline at a 0.5 compression ratio. Additionally, TokenSkip ensures adherence to the desired compression ratio while preserving strong reasoning capabilities, resulting in a 1.8 times speedup in average latency. Overall, TokenSkip's approach of pruning redundant tokens enhances COT efficiency without compromising the interpretability and effectiveness of the reasoning process.
How did you validate the effectiveness of TokenSkip in your experiments? What datasets were used, and what metrics were employed to assess its performance?
The effectiveness of TokenSkip was validated through extensive experiments using two widely recognized reasoning benchmarks, GSM-8K and Math 500. Specifically, we evaluated the performance of TokenSkip on the 5-instruct series, where it achieved a 40% reduction in token usage on GSM-8K with less than a 0.4% performance drop, and a 30% reduction on Math 500 with a performance decline of less than 4%. The metrics employed to assess TokenSkip's performance included accuracy, the number of caught tokens, and inference latency per sample. Additionally, we compared TokenSkip against two baseline methods, prompt-based reduction and truncation, to demonstrate its superior adherence to specified compression ratios while maintaining strong reasoning capabilities. The results indicated that TokenSkip not only preserved reasoning performance, but also provided significant speedups in inference latency, validating its effectiveness as a caught compression method.
What are some of the limitations of TokenSkip that you encountered during your research, and how might they affect the application of your method in real-world scenarios?
One limitation of TokenSkip is its reliance on the LLM LINGUA2 model for token importance measurement, which, while cost-effective, may not capture all essential information needed for optimal token pruning, potentially leading to suboptimal compression performance. Additionally, the experiments indicated that at lower compression ratios, 0.3 and 0.4, the adherence to specified ratios significantly degraded, suggesting that excessive trimming could result in the loss of critical reasoning information. This could hinder the effective training of LLMs to learn caught compression, impacting their reasoning capabilities in practical applications. Furthermore, while TokenSkip shows promise in enhancing reasoning efficiency, the computational overhead associated with training and fine-tuning models remains a concern, particularly for larger LLMs. Lastly, the empirical results suggest that while larger models perform better at identifying shortcuts, the scalability of TokenSkip with even larger models has yet to be fully explored, which may limit its applicability in scenarios requiring high-performance LLMs.